Hi, I'm Andrew, and this is my presentation on guitars. This is a guitar pickup, and this is what captures the sound of the guitar and is able to transmit it to the amplifier. Guitar pickups have a magnet inside of them, as you can see here, and on either side of the magnet there are separate pole pieces that are magnetized by the magnet. And in each of the two sections here there's a coil of copper wrapped around it. Now, guitar strings are magnetized and they have a north and a south pole. It is a fact that whenever a magnet moves towards or away from a coil of wire, there is a resulting change in flux and the magnetic field. This is how guitar pickups pick up the sound. When the string isn't moved, there is no change in flux and the magnetic field is equalized. When talking about electromagnetism of guitar pickups, it's important to remember the right-hand rule. The right-hand rule is you put your hand so that your pointer finger is pointing the direction the magnetic field from the strings would go through the coil. And from there, the thumb represents the direction of the current. In this case, it would be counterclockwise. And this finger represents the direction of the magnetic field outwards. Whenever the magnetic field sent by the string into the pickup is greater, the resulting current is greater also. And when it is smaller, the current is smaller. And this is what creates the change in flux. Nodes are the areas of the string with no displacement. You can see nodes because they are the points where the string moves the least. On a guitar, there are two of these points on either side of the string when you're playing a string open. And you can see those are where it moves the least. Antinodes, however, are the opposite. Antinodes are areas on the string where the string moves the most and experiences the most displacement. As you can see, the antinode is around here in the middle of the guitar because that's where it moves the most when it's vibrating. If you look at a string while it's vibrating, you will note that there's only one antinode, and it's around the middle of the guitar. And this can lead you to infer that the string only has one wavelength. For a string, whenever you cut the wavelength in half, you must double the frequency. This is demonstrated by the equation velocity equals wavelength times frequency. If the speed remains the same and the wavelength is halved, the frequency must be doubled in order to compensate for the change in wavelength. Now, whenever the frequency is doubled, the sound, in musical terms, goes up an octave. The first full change in octave on a guitar string occurs on the 12th fret of the guitar. But you can keep on having the length of the string by having the wavelength. The inverse of this is also true. If you double the wavelength and the speed remains constant, the frequency must be halved. I will now demonstrate how, in having the wavelength, the frequency is doubled. Here on the open bottom string, it sounds fairly low, but whenever you cut the string off right here, it's the same sound, but an octave higher. If you keep on going to about here, it goes up again. And over here again. Conversely, whenever you double the wavelength, the frequency is halved. The speed of a wave depends on the tension of the string. A wave will move faster through a higher tension string than a lower tension one. Now, it can be inferred that if the speed of a wave is higher, the frequency will be higher since the wavelength remains constant. And since the frequency is higher, the pitch is higher. And I'll demonstrate this by plucking two different strings of different tensions. The string here, known as the B string, has a much lower tension than this string called the E string. And as you can see, when I pluck them at the same time, the one with the higher tension has a higher frequency or pitch than this one. When two notes have a slightly different frequency, their corresponding waves will not line up. When this happens, the waves cross at certain points, and whenever that happens, you will hear a little bump or distortion in the sound. This is called beat frequency. Beat frequency is the result of a difference in frequency of up to 7 Hz. When there is this difference, your ears can pick it up as a pulsation of loudness. I will now play two slightly out of tune notes. You can hear the ruptures when they bump together. This is called beat frequency. Guitarists can use this to determine how to tune strings, because the closer the two frequencies get to each other, based on how the tension of one of the strings is adjusted, the faster the disruptions get until they are non-existent. Because the two notes have the same frequency, they are overlapping as a whole, not in occasional spots in the wave, so there are no disruptions. This is how guitarists often tune. Thanks for watching. I hope you've realized just how complex guitar pickups are.